Okay, CEA. We're back doing video number 2 for our beam design. Last time we got to the point where we figured out how much we need to find a beam that will hold 67,635 foot-pounds of bending force, even though our beam only is going to be exerted to 40,500 pounds by our design, because we have to add in our safety factor. Okay, so that was our step 5. So if you look back here, we've gotten to here. Now we need to calculate the required plastic section modulus. So remember, we talked about how steel beams can be, well, anything really, not just steel, but anything has a certain amount of elasticity. That means you put a load on it and it gets stressed and often strained, which means it gets misshaped. It starts to bend. And when you take that load off, if it's elastic, it will bend back, or it will go back to its original shape. If you put too much of a force on it, often it will be taken out of shape enough that it won't go back. So once it reaches a certain point, it loses its elasticity and becomes more what we call plastic. And so what this is a measurement of elasticity in beams. You don't really need to know a whole lot more than that right now, but how you do this, okay? Let me just get myself squared away here for a second. There's another formula. So we did this one to find our allowable bending moment, and then we turn this over, and this is going to be our plastic section modulus. Okay, so we use this formula, for our next step. So we just figured out MN, and at the very beginning of this, I should have shown this to you guys, but at the very beginning of this little exercise, I got a lot of papers. They gave us these facts, right? They gave us our dead load and our live load, which we've already used. They told us our Fy, which is a measurement of steel strength, is 50,000 psi, and they told us that our floor will be supporting a plaster ceiling. And down here, they tell us that our 29 million psi for steel structure is our E. This will all come into play later. It'll all make sense. But anyway, they give us this criteria. So this is our Fy for this formula right here. And we already know Mn because we just figured out in our last calculation. So here we are with, excuse me, with number 6. And our formula is Mn equals Fy times Z to the X. Okay, so Mn, we know that. That's 67,635 foot-pounds equals 50,000 psi times Z to the X. So now, algebraically, gosh darn it. Algebraically, this is pretty easy to solve. If I divide 635 by 50,000, I should get my ZX. However, I have, PSI and foot-pounds are not the same thing. And in this class, we've had equations, and then we cancel out different types of units and come up with a final unit. And that's what happens here as well. But in order to do that, we have to convert our foot-pounds into inches. So anyway, we have to multiply this by 12, okay? Because of unit issues. So it's not really worth me going through all the math. I can do that another time. But what we're going to do is we're going to take 67,635 times 12 and then divide it by 50,000. Okay? And we will come up with Z to the X, and this will be in inches cubed. Once we do all the canceling, so this 12 is 12 over 1 for, and that represents inches over feet. And then your feet cross out with your feet here. And I don't want to go through all of it. But anyway, this will be inches cubed. Okay? So if we do that, I'm going to say 67,635 times 12 equals 811,620 divided by 50,000. Divide that by 50000. And you get 16.2324. So we're just going to round to 16.2. And that is inches cubed. So that is our answer for number 6, which is what is our plastic section modulus. So we need a plastic section modulus at least 16.2 inches cubed. So what that means is, I'm going to go ahead and switch off of this, and I'm going to switch here. And in our project Lead the Way, we're in 3.2.6. In the equipment, they supply a web page, which is this web page. It's structuraldraftingexpert.com. And we need to go in there and we need to use our plastic section modulus that we just figured out. We go to our steel sections right here, and then we scroll down and we go to wide flange steel beam. And in there, you can see that they have for these beams dimensions and properties. We want to be on the properties page. And what we do is we come over here, here's our plastic modulus, and we take our Z to the X. And we scroll down. Now we had 16.2 was what we figured out. And we need to scroll down. See, these are really big numbers, but these are huge beams if you look at these numbers. Okay? And we're going to scroll all the way down, and we're going to find a number that is 16.2 or higher, but as close to 16.2 as we can get without going under. So we're getting closer here. We're getting closer. There's a 17.4. Is there anything that's closer to 16.2 without going under 16.2? There's a 16 and a 12, and nope, looks like 17.4. Looks like this beam is what we need. So that's going to be, if I switch back to my thing here, that is going to be my, and I think that's our next step on this. If I show this, it says we figure out our plastic section modulus. That was our 16.2. 7 is going to be choose the beam. That is what we're doing right now. So this is 7, and that's going to be a W1214. Okay, so everything we've done to this point is getting us to where we can choose the beam that we think we need. Okay, and we want to leave this open over here. We want to leave this open because we're going to use this chart again here in a minute. So now what we do from here on out is we make sure we go back and we check this particular beam with all of its attributes listed in this chart. Make sure that it will stand up to the shear, make sure that it will stand up to the bending moment, and make sure that it will not deflect too much. So if it meets all three of our checks, then this is the beam we would use in that application. If it fails one, we have to choose another beam and then recheck it. Okay, so we would choose another beam with a plastic section modulus close to 16.2 and see if we can get that one to work. So here's the first. We're only going to be able to do probably one of these checks, maybe two of them in this particular video. So the first check that we do on it is check for shear capacity. Okay, and the way we do that again is by using a formula that I gave you in your packet here. It's going to be right here. So we're going to use this. We're looking for Vn. Our shear capacity has to meet the shear plus a safety factor. Just like we did before with bending moment, we have to figure out what we have to hit, and then we'll come over here for the next step and actually figure out whether we hit it with this beam. So these numbers in here come from the beam. This is getting us what we need to reach for our shear. So we're going to go ahead and do that for 7, or for 8, I'm sorry. So now we are figuring out our shear capacity. So our formula is Vn it must be greater than or equal to Va. Now we already figured out Va, and we already know our omega here, because our omega is right here. It's one. That's our safety factor always, 1.5. So I'm going to put omega times omega. So our Vn is going to equal our Va. Well, our VA was our shear that we figured out way back here, okay, on our number 3, 9,000 pounds, okay, but it's actually going to be, I believe, our total for this beam, not 9,000. It's going to be the 9,000 on. No, that's not right. It's on the one side. So we're gonna go here. Vn is greater than or equals to our 9,000 times our safety factor of 1.5. And so our Vn is going to be greater than or equal to 13,500 foot-pounds. So we have to find a beam that will handle at least 13,500 foot-pounds of shear on each end, just like we had to find a beam that would handle 67,635 foot-pounds of torque. And I put foot-pounds down here. This is just pounds. It's just pounds of shear. I'm sorry. Okay? So, number 9 is what we will do next. So, the next formula is this formula. So, Vn equals 0.6 times Fy times AW. Okay, so we know Fy, they gave that to us at the very beginning, so the Vn is going to equal 0.6 times 50,000. Now AW is one we got to figure out. That is the area of the web of, and it'll tell you right in here, the area of the web of an I-beam. So an I-beam looks like this, right? The area of that web, you got to take the thickness right here and multiply it by the height, and you will get the area of that web. So what we do is, and you can get those numbers, I'm going to erase this because it's in my way, but you can get those numbers off of your trusty chart here. Oops. So when I come here, if say I had 1214. So what'll happen is when I come up here and I need to go to my dimensions, I got to scroll all the way back down to my 1214. And here it is. And what I want to look at is the thickness. So my AW is going to be TW D times TW. And here's my D right here. And here's my thickness. I like using the decimals because if you use the fractions, in order to multiply them, you got to turn them to decimals anyway. So here we are. We're going to say 11.91 and 0.2. So if I come back to my formula here, it's going to be 11.91 times 0.2. So when I do this on my calculator, I say 0.6 times 50,000. Well, I better do this first. 11.91 times 0.2 equals 2.382. So this is 0.6 times 50,000 times 2.382. So here we go. 50,000 times 0.6 times 2.382 equals, and I get 71,000, so Vn equals 71,460. And what am I going to have here? This is going to be pounds. So this is the last thing and I'm going to be done with this video. My beam, this beam will handle 71,460 pounds of shear. That's what we figured out here. That's why we went in and got these numbers, because the size of that beam helps determine how much weight it'll hold, right? We only need to hold 13,500 pounds of shear. So this beam, because we hold so much more than we need to by design, this is jacked up because we have our safety factor in there. We only have to hold 9,000 by design. This beam is going to be definitely good in terms of shear. So you just write good next to it. This is all we did here, is check to make sure that this beam will hold our required shear plus the safety factor. All right, so we'll do the last two things on the next video.